air traffic control in the 90s. Handling on average over 700,000 aircraft a year, this busy air traffic control centre at Maastricht in the Netherlands is often stretched, working to capacity. For many years it has been recognised that the availability of a two-way digital data link between aircraft and air traffic control would yield significant improvements in flight planning, in addition to monitoring and control communications and operating efficiency. However, the solution to the problem has rested not only with the aircraft manufacturers, who have already made leaps and bounds in aircraft efficiency, but with organisations such as Brussels-based Eurocontrol, the European Organisation for the Safety of Air Navigation. The datalink capability of Mode S, which stands for Selective Address, might well be the possible means of improvement.
The Mode S datalink that we're discussing today is a development of the conventional secondary radar. I think the large part of the work done on the Mode S development started under a much different name. In the United Kingdom, it started under the name ADSEL, which was Selective Address, and there was parallel work going on in the United States, where their system, which was very similar indeed, was called DABS, which was a discrete address beacon system. And in the towards the end of the 1970s, work that was being done in both areas was brought together and combined under what was known eventually as the Mode S system.
October 1991 saw the culmination of that work when they established the feasibility of the use of a Mode S data link for air navigation. It was to be a world's first.
Flatbox 05, squawk 4537.
453705, we're ready on turn for takeoff.
05, roger, after departure, climb on track, not above 1500 feet, on the Bedford QNH 1003.
I'm on track for about 1500 feet on QFA 103,
05, that's just confirming it's the QNH is 1003.
That's copy.
The demonstration required the modification of a BAC 111 testbed to accommodate a Mode S transponder. The datalink module was added to achieve more effective communications capacity, better intelligibility, higher integrity, and better computer capability. Also installed in the aircraft is a processor that provides an interface to the aircraft avionics, a datalink processing unit, and a general-purpose computer that provides an interface to the pilot's selector panel and screen that forms the airborne end system. On the ground, the communication lines connect the controller to the DALAP via the ACE processor at RSRE Malvern. In our demonstration, a further application capability accommodated Volmet. Both airborne and ground systems are in turn connected to one of two available Mode S interrogators, one at Gatwick and the other at Malvern, the latter being the station used to interrogate the aircraft as it flew its predetermined flight plan over eastern England and the North Sea. The demonstration, performed in two halves, simulated two distinct ATC scenarios.
During the first scenario, there was no actual data link dialogue between controller and pilot. What was happening was a large amount of data was being transferred via the link, which related to the selected inputs to the flight system and also dynamic data from the avionics system on board the aircraft, and these were used by the ground system and by the controllers in order to get a good indication as to what was happening on the aircraft. The main difference between the first and second scenarios was that in the second scenario we were also transferring the normal dialogue between controller and pilot via the data link. So during the second scenario, or the inbound flight, all of the control instructions were passed via the data link, and it was this which was regarded as being the world first in the use of the data link for controlling an aircraft in controlled airspace, entirely by means of data link. No RT was used, although we must stress the RT channel was always there, available for both pilot and controller to use in the case of non-routine situations, and I think this will be the case for very many years to come in the future.
Before exploring the practical aspects of the demonstrations, let's first examine the individual elements involved more closely. The Mode S ground station at Malvern simultaneously provides surveillance and data link communication with the transponder on board the BAC-111. Ground lines connect the Mode S station with the DALAP, the data link applications processor at the ATC evaluation unit at Herne on the south coast of England. All the ATC communications, including accessed VOLMET information, pass through the ACE processor at Malvern and onto the ATC system at Bedford. At Bedford, the main feature of the demonstration is the STANS ATC simulation facility, which is a functional, quick prototyping tool used for the testing, simulation and evaluation of advanced ATC decision-making aids. The simulation facility is based on the zone of convergence concept. The workstation consists of a centrally mounted medium-resolution color terminal that presents the radar picture. To the left can be seen the data link ground terminal display. This electronic data display provides the controller with an aid memoir. In addition to indicating when the clearance has been confirmed, this confirmation is also shown by the removal of a yellow overlay that indicates the receipt of the message in the aircraft and that the autopilot setting matches that clearance. If it doesn't, then the clearance remains highlighted in yellow. In addition to standard RT used in Scenario 1, the controller also has at his or her disposal a digital ground-air-ground communication channel provided by the Mode S data link. Instructions to the aircraft are implemented via a conveniently placed digitizing tablet. The display presented to the controller contains several simulated flights along with the actual position of the BAC-111 test aircraft, now designated Nugget. In addition to the controller's workstation, a monitor simulating the BAC-111 autopilot settings was available to illustrate what was happening on the flight deck. On board the BAC-111, the Mode S transponder receives and transmits data link information, which is in turn interfaced directly to the aircraft avionics and data link processor. The data link processing unit enables automatic extraction of information from the aircraft systems, as in Scenario 1, in addition to the handling of ATC instructions and acknowledgements and VOLMET interrogations in Scenario 2. The pilot DLPU interface in Scenario 2 being handled by the onboard general-purpose computer. In addition to the flight deck instrumentation, the conventional map display indicating the aircraft's route also contains an alert indicator informing the pilot of an uplinked ATC instruction. The data link information for Scenario 2 is displayed on an experimental LCD panel mounted in the center of the cockpit, below the autopilot, where all ATC and VOLMET instructions are displayed. In the center of the screen, there is also a flashing alert each time a new instruction arrives, the latest ATC instruction appearing in the central part of the screen. As soon as the pilot depresses the acknowledgement button, the instruction transfers to the appropriate clearance box so that all current clearances are displayed. At the top of the LCD display, the latest volmet data requested by the pilot is also displayed, replacing the synthesized voice of conventional meteorological information. A small printer situated in the central pedestal offers a hard copy if required. Let's now see these elements at work in the context of the demonstrations. Having now adopted for scenario 1 the call sign Nugget 1, we will concentrate mainly on the use of the EDD screen. Still utilizing conventional RT, respective instructions are first radioed to the pilot and acknowledged in the normal manner. At the same time, they are inputted via the digitizing tablet.
Okay, I'm replying to her instructions. I'm also dialing these settings on the autopilot. They're going to the data link processing unit and being downlinked to her on her screen.
Nugget 001, roger. Climb flight level 130.
These clearances are, at the same time, displayed on the electronic data display with the respective instruction highlighted in yellow. This acts as an aide-memoire. When the autopilot setting matches the clearance and the confirmation is downlinked, the yellow overlay is automatically removed. If the autopilot setting does not match the clearance, then the instruction remains highlighted in yellow.
Scandinavian 342, descend flight level 290.
In the experimental setup for the Mode S datalink demonstrations, the STAN system, besides constituting the ATC N component of the datalink with the BAC 111, also provides additional simulated traffic with equivalent airborne equipment to present the controller with a realistic ATC environment. Instructions and acknowledgements are displayed on the EDD in exactly the same manner as our test aircraft.
0 knots, Scandinavian 342.
Nugget 001, climb flight level 170. Speedbird 258, fly IAS 280 knots.
Nugget 1 is now on its way to flight level 170, as can be seen by the absence of the yellow panel. The climb rate is 2,400 feet per minute, and the aircraft is passing through flight level 140. Its heading remains 090 and its airspeed 300 knots.
Descend flight level 100.
Once at flight level 170, another instruction is given to continue to flight level 230. So let's see the sequence of events again.
Nugget 001, climb flight level 230.
The aide-memoire indicates that 230 has indeed been instructed.
Climb flight level 230, Nugget 001.
Having reset the autopilot, the confirmation is downlinked along with other avionics data, and the aide-memoire yellow overlay is removed.
Speedbird 016, resume air navigation, direct Papa Alpha Lima.
Notice the relevant climb rate and present altitude being constantly updated via the data link. The update occurring at each sweep of the radar antenna at Malvern. Data from the simulated traffic is also updated in a similar manner. Being clearly displayed, The constantly updated data from all traffic enables the controller to know precisely the status of each aircraft.
Nugget 001, resume air navigation, Alpha Juliet Hotel.
Nugget 001, that's down Alpha Juliet Hotel.
Having now been instructed to proceed to Alpha Juliet Hotel, Scenario 1 is almost complete. Once the aircraft is passed on to another sector or controller, in this case handed back to Approach Control Bedford, the aircraft label on the EDD screen is cleared.
Nugget 001, continue now with Bedford. Bye-bye.
The end of the first scenario, or the end of the outbound leg, the aircraft actually passed outside the coverage of the RSRE radar at Malvern, and during this stage we actually made the changeover in the ground system to transfer from the first scenario to the second scenario.
The datalink processing unit, until now processing only avionics data, is ready to assist with a quantum leap into a new era of air traffic control. Having re-established radar contact, all is ready at Malvern. The controller, used to the cacophony of sounds in a busy air traffic control center, now prepares to issue silent commands to the redesignated Nugget 2. On board the 111, the pilot awaits the alert signal. The LCD panel is about to come to life. Acknowledging the instruction and then setting the autopilot, the 111 begins its acceleration to 280 knots. The command is transferred to the relative box on the LCD, and the downlink confirms the action to the controller, and then new, voiceless instructions. For the purpose of this film, what you have just seen is an edited sequence of events. Using a rotating antenna, the delay between the controller releasing the instruction via the datalink and the pilot acknowledgement and implementation was approximately 22 seconds, much shorter than depicted here. However, a number of measures are under consideration to reduce this delay, a prerequisite for the link's future use. Now almost halfway through the second scenario, Nugget 2 requests Volmet information from the Volmet databank at Malvern, and the uplink data is displayed along the top of the LCD. A course correction is now instructed, received and acknowledged. The autopilot is set accordingly. Confirmation is received by the controller as the yellow box disappears from the screen. As flight level 100 is instructed, let's examine the sequence in more detail. The input instruction to descend is confirmed in a strip at the bottom of the screen prior to execution. The aircraft label changes accordingly. On the EDD screen, the instruction being passed to the aircraft is highlighted in yellow. Now being uplinked by the DALAP and ACE processors, the instruction arrives on board the aircraft via the datalink processor. The pilot is alerted on his map display at the same time as the datalink message alert is activated on the LCD. Pressing the acknowledgement button, the new instruction transfers to the altitude box. The autopilot can now be reset. Now being downlinked via the datalink processor and on the ground processed via the DALAP and ACE processors, the acknowledgement is passed to the controller and the yellow overlay is removed. The feasibility of the use of Mode S datalink has more than been proven in the demonstrations, but of course many refinements and improvements are necessary before the implementation of such a system. Maurice Cox sums up the future of Mode S in the context of the EASY program.
The name EASY is an acronym for a program of work which relates to enhanced air traffic management and Mode S implementation in Europe. And this had two main aims: one, to lead to the implementation of Mode S, and secondly, to the provision of an aeronautical telecommunications network within a core area of Europe, the core area being an area in which the number of traffic movements is very, very high indeed. And within this, the Mode S data link will play a very important part. Having the aeronautical telecommunications network, however, does mean that it will be capable of accepting data transferred from aircraft via the other sub-networks, as we call them, which are different forms of data link, namely the VHF data link and a satellite data link. And in other forums, the use of the satellites and VHF is being considered as alternative data links. And indeed, within the EASY program, they are considering the, if you like, the integration of the other data links within the aeronautical telecommunication network. The demonstration has shown the maturity of the Mode S technology. Within the Eurocontrol organization, work is now in hand to lead to the implementation of Mode S and the ATN in a core area by around the turn of the century. Eurocontrol is now facing a very exciting challenge to exploit these as effectively as possible for the benefit of the air traffic services of tomorrow.